The Sci-Mic stage. We've been talking to scientists all day yesterday. I am so excited to welcome to the Sci-Mic stage one of my favorite scientists of all time, Edgard Rivera-Valentín, Dr. Edgard Rivera-Valentín.
What's up?
Yeah, we hung out. We hung out at the SACNIS conference in Puerto Rico last year.
Yeah.
Yeah,
I came home. We chilled upstairs. It was great.
We had the very vibrant outfits on, but but for the conference, very tame.
Yes.
Yes, and it was amazing. And the reason we connected so well is because we're both astronomers, and we talked about a lot of astronomy that was happening on the island or was in the past and had stopped. So that's actually the first thing I'm going to talk to you about, because I know that you're passionate about the observatory. So can you tell us a little bit about the astronomy that was happening at Puerto Rico, and like, I'm going to just let you take it. I don't want to color the story.
Okay, so Puerto Rico is known across the world because we had the world's largest, most powerful, most sensitive planetary radar at the Arecibo Observatory in the city of Arecibo, where I was born and grew up. The primary reason I'm in planetary science is because as a kid, when you go up there, it's just awe-inspiring.
It was huge.
Yeah.
Yeah, it was beautiful.
When you stand up there and overlook at this 305-meter dish, this marvel of engineering, which isn't just about like, oh wow, think about all of the people that came together to build this. It's also about, think of all of the really neat science that has been happening here in my backyard.
And as a kid, you're like, we're talking to space, or I'm hearing space in my backyard.
Yeah.
Yeah.
I'm looking at asteroids. I'm shining a light.
Yeah.
Shine bright like a diamond style. It was great.
I wanted you to break out in song, but
I was close.
I know, so I could feel it.
Held it back for a bit. But in Puerto Rico, the Arecibo Observatory was our biggest connection to astronomy. We have other observatories across the island at the University of Puerto Rico system. These are smaller optical telescopes. They still play an important part in studying asteroids, but compared to the grand scale of the Arecibo Observatory, it's just like, it's obvious, right? In Puerto Rico, the observatory was a significant cultural icon, right?
Yes,
When on the island and you talk to a Boricua and you say, hey, science, they go, have you been to the observatory? Because you should go to the observatory, right? It's also like all over our art. But sadly, in 2020, amongst all of the other chaos that the universe is throwing at us, the platform over the dish ended up snapping, breaking, and there was a collapse. And then as of August 2023, science operations at the observatory ended. So let's do a little flash backwards.
Baby back in time.
Yeah, baby back in time, 2017. There was another disaster that happened in Puerto Rico, Hurricane Maria. And something that taught us or reminded us as a community could be seen in social media, where we were all using the hashtag Puerto Rico se levanta, Puerto Rico rises. And so, although there was a catastrophic loss of the observatory, after that, there's been a lot of people that have come together to make sure that the island still has a tie to astronomy, tie to planetary science. Desiree Cotto Figueroa has started a new astronomy minor at the University of Puerto Rico, Macau.
Wonderful.
Abel Mendez has an astrobiology program at the University of Puerto Rico, Arecibo. The main campuses in Rio Piedras and Mayagüez have also started a program supporting radar and radio science. So, Puerto Rico se levanta. It's what our people do.
That's so beautiful. You're like, this could be a really sad story, which it is.
Yes.
But I'm going to end on hope. And I remember talking to you at the previous conference, and you explained to me how we actually use radio astronomy to detect and like verify that asteroids are coming towards us or just in our neighborhood. Can you kind of break that down for us?
Yeah. So like in astronomy, when people think of looking up at stars, you go outside and you take out your telescope and you point it and you're waiting for this stray photon that was launched from this star that's been traveling for millions of years, right? Yeah. To randomly find its way into your telescope, to randomly hit your eye so your brain goes, ooh, shiny, right? That's how astronomy typically works. But in radar, we're impatient. We're like, I'm not waiting for any of this. Instead, we have basically a big flashlight attached to our telescopes, except it sends light out in radio wavelengths. We send that light out, it hits an asteroid or planet, bounces back, and because we know what we transmitted, we know that light really well, any change is because of the object, so we can measure things super precisely. So for like an asteroid, when we're studying it with radar, these things are typically 100 millions of kilometers away. I can tell you that distance down to a meter.
Wow.
Right?
That's fascinating. Okay.
And they're typically moving dozens of kilometers per second. We are basically the police force of the solar system. We're like dozens. I can tell that speed down to centimeter per second. Wow. That's important if you want to be able to understand where this object is going to be out a couple of hundred or even 200 years into the future, because you want to be prepared. We, unlike the dinosaurs, have NASA, ESA, JAXA. We can actually prevent devastation.
And I want you to know that it was not lost on me that a radio astronomer was slightly dissing an optical astronomer like me. But let's move on. Let's move on, and let's talk about what you are doing now. What is your current research on? Let's talk about that.
So right now I'm working at the Johns Hopkins Applied Physics Lab. I'm continuing doing radar with Arecibo data. So there's many years worth of observations that we have that we're still combing through to better understand Mercury, the moon, different asteroids. But radar is also a technology that we're sending out into space on spacecraft. The Lunar Reconnaissance Orbiter has an instrument called MINI-RF, Miniature Radio Frequency Instrument, and so it's also transmitting radar, hitting the moon up close. We're looking for ice in buried craters, or not buried craters, but permanently shadowed craters, so that if and when we send humans back to the moon, they might be able to go and use that water, because I'm thirsty right now and water is important, right? We also have different radar instruments orbiting Mars, and we're thinking about what the next radar instruments should be that we send out, but also the radar instruments that we should then be developing on Earth after the wake in terms of science and observing and culture that was the collapse of Arecibo.
Okay, so I think a lot of people don't understand that certain telescopes have so much data. There's discoveries that are happening from looking at Venus from 30 years ago. People are still looking at that data. So sad. It's very sad that Arecibo is not there, but it has all this legacy or this history that you can still kind of comb through.
Yeah, exactly. The legacy of Arecibo is twofold. It's our data that people are still using to better understand the universe, to better defend the world from devastation, but it's also that legacy of inspiration. And so one of the things I try to do in my job is to, although the telescope isn't there, make sure that we are showing people the value of what Arecibo brought to the table, what ground-based radars bring to the table, to continue inspiring future generations.
Well, let's talk about the future. What are you most excited about? So you're saying you have all these new projects. What is your dream? What is your dream for the next step of radio astronomy?
So currently, the active facility that we still have zapping asteroids is the Goldstone Solar System Radar in California.
Okay.
That is part of a NASA facility. And the technology that is still running it, we're talking about my mother may not have been born yet kind of thing.
Oh, wow.
Right? But since all of that time, we have continued to develop radar technology. We just haven't gone back and applied it to ground-based facilities. So I think the biggest next step is to take a lot of these new technologies that have been developed for radar and now say, instead of just using it to, for meteorology, to track aircraft, let's point it back out to space and see if we can better pick up those asteroids, right? Because the more asteroids we pick up, the better we're prepared.
I mean, and that goes to the theme, right? Towards science without walls. So perfect.
There's no walls in space.
There are no walls in space, unless you're in the space shuttle.
Unless you're in the space shuttle.
So you're talking about using data, using technology from other fields, and kind of retrofitting that to what we've been using, what we want to use.
Yeah, we're looking at what should be the next ground-based facility, what should be the next spacecraft radars that we're sending out, and how can we incorporate all of these new awesome gizmos into what we do.
We have so much more time. You speak so fast. So what we're going to
Okay, so did I mention I'm Puerto Rican and that we all have the fastest Spanish dialect? I'm holding myself back in speed, okay?
You're just doing it for me.
Yes.
Thank you. Thank you. Let's actually go back to what you were talking about with moon craters and water, because I think that's really fascinating, and I think a lot of people don't know about this, because they think about like the dark side of the moon. There is actually no dark side of the moon.
Correct.
Do you want to break that down, and then we'll talk about how these craters do not see light, which is not the same thing. These are two different things. So go ahead.
Okay, so the moon actually rotates.
Whoa!
What?
So I had a professor, and did somebody clap for that? I hope they did. I had this professor, and he was like, okay, the middle is Earth, and I'm the moon, and I'm going around you, and I'm facing you, the one side faces you the whole time. But I'm still rotating, just very, very slowly. And I was like, that's brilliant.
And I did that with a lot of the kids that came to the telescope, because that is like the best representation of what we mean by rotation, right? The moon is still rotating, it's just we're always seeing the one side of it.
Yeah.
So it still goes through day and night cycles all over the place. We're just not seeing the backside. And because we don't see the backside, we're like, that's the dark side. It's mysterious.
No, but sun gets there.
But sun still gets there. It still shines bright. It's cute.
So why are these craters never seen sun? Parts
So-
of the craters.
Some of these craters at the poles have just the right geometry so that when the sun comes in, the crater wall stops it from getting into the crater floor. And so those floors get ridiculously cold.
Yeah. And so I'm just going to tell you a fun fact, and I want you to be impressed by me.
Demon.
Okay, so I was talking to a planetary scientist, and she was saying that, for those of you out there that might not know, the moon was created at basically the same time as the Earth. Because in the proto-Earth, there was something almost the size of Mars that came in, smashed it, and then all of its smashed bits kind of congealed or whatever and turned into the moon. And she said that if we had water before that, Mars-shaped thing smashed into us, all the water would have been vaporized.
Yes.
And so if we didn't have the moon, we might have been like a water world, and we would have had even more water. Is that correct?
That is one of the lines of thinking about this. But
Another one.
the thing is with any of these type of simulations is we only have so much data. The Earth has only retained so much of the ancient record. And so when you're putting this together in part, you're almost being a storyteller, trying to see, okay, what part of this makes sense? But I don't have a time machine. I don't have the TARDIS. You have the TARDIS? Why are we here?
We're going to talk about that afterwards, offline. Go ahead.
Okay.
Continue.
But like if I had a TARDIS, I could actually go back in time and actually totally watch it. So we have hypotheses. Some of them have led us to these type of ideas where some of the water, if that impact wouldn't have happened, maybe Earth would have been a water world. But some others say that there wouldn't have been sufficient delivery of water into Earth to let it be a water world. But
Wow.
we just need more data. That's part of science. We're discovering things.
Yeah. So I'm going to, last word, what do you hope for, what?
Last word.
Last word, ever.
The-
What do you hope, you said for radio astronomy, but what do you hope for astronomy? What are you most excited about for astronomy as wide as you want it in the next 10 years? Yeah, I'm going to make you do that. Now we're not talking fast.
That is wide. I'm going to talk for more. So, for astronomy as a whole, I would like to better understand the distribution of exoplanets in the galaxy and how habitable they are. For my field and specifically for radar, I want to be looking at what I am looking forward to.
Yeah.
I'm just going to be hopeful. I am looking forward to those next facilities that will come up. Green Bank Telescope is currently looking to add a radar into their system that's called NG Radar.
That's in Virginia.
That will be in Virginia and West Virginia. They're going to be looking to pair up with what's called the Very Large Baseline Array and the NG Very Large Array. They love their acronyms.
These are arrays of radio telescopes,
Yes.
of dishes.
And so looking forward to that facility, looking forward to the Goldstone Solar System radar being updated, looking forward to even another radar being added because you can't have enough radar. Radar is awesome.
Yeah. Go astronomy.
Go astronomy.
Thank you so much for talking to me. This was the best.
Gracias, always.